Welcome back to the deep dive. You have that remarkable feeling when you switch cognitive tasks almost effortlessly.
Mm,
So maybe you're deep into a complex spreadsheet 1 minute, and the next you're out on a hike, and you instantly identify a bird call.
right.
Your brain just handles those wildly different domains, logic versus pattern recognition, without needing a full reset.
That incredible fluid adaptability is, well, it's fundamentally rooted in what we call the biological nervous system, or BNS.
The BNS.
And it achieves this because it doesn't rely on some monolithic fixed structure for every single task. Instead, it dynamically regulates synaptic plasticity,
Okay.
and it activates distinct, optimized regions of the brain, depending on what you're doing. It's a master of flexible resource allocation.
And that, right there, is the core problem we're digging into today. Why can't our most sophisticated AI models, specifically meta-learning models, do the same thing? I mean, meta-learning is supposed to be learning to learn, right? It finds a strong initial setup, a global prior, to quickly adapt. But it forces that learning to happen inside a totally fixed network.
Precisely. Standard meta-learning is excellent at finding that good starting point, the initial weights. But then it says this one template must be used for everything.
Whether it's simple or complex.
Exactly. Whether the task is simple character recognition or, high-dimensional robot control, it's like trying to use a deep-sea submersible to cross a desert highway.
The tool is powerful, but just completely wrong for the job.
Structurally compromised, yeah.
So our mission today is to explore the research that's proposing a fix for this rigidity. We're deep diving into flexible network structure, or FNS, why the evidence says it's essential, and the proposed solution that mimics the BNS, neuromodulated meta-learning. We're going to show you how they're trying to force AI models to stop being these fixed monuments and start becoming, well, adaptable chameleons.
Okay, so let's unpack this inflexibility.
Yeah.
The analogy between the BNS and standard meta-learning, it starts out pretty strong because they both share that concept of a global prior.
They do. That's the starting line for learning quickly. For our brains, the BNS provides that prior. It sets up the general wiring and synaptic strength.
And for meta-learn.
For meta-learning, the prior is just the set of initial weights the model starts with before it tackles a new problem.
But the moment the task changes dramatically, that fixed structure becomes a huge bottleneck. The BNS activates different regions, different structures. The standard models, they just stick to one size, one topology for everything.
So how did the researchers actually prove this was the problem?
Well, they ran these exhaustive tests across a huge spectrum of different structures. They used 4 benchmark data sets: Mini-ImagineIt, Omniglot, Tiered ImagineIt, and CFAR-FS, which, represent tasks from super simple classification to really complex photo recognition.
And crucially, they paired these with different deep learning backbones.
Yes.
Now, for anyone listening who hasn't been tracking neural net evolution, can you just quickly clarify what those backbones are? We hear names like Conv4, VGG16, ResNet.
Of course. You can think of them as different types of chassis for the AI. Conv4 is a classic. It's lightweight, shallow, very low computational cost.
And ResNet.
ResNet is on the other end. It's a massive, deep architecture. It's what's often used for state-of-the-art image recognition, and it needs huge computational resources.
So by testing all of them across these different data sets, they were basically measuring the cost-benefit of different structural choices.
Exactly. And here's the crucial nugget they found.
What's that?
The optimal model structure changes depending on the data you're analyzing. There's no single fixed structure that excels at everything without just massive waste.
That seems so obvious in retrospect.
It does. A perfect example is comparing Omniglot and Mini-ImagineIt.
Okay.
Omniglot tasks are simple, just classifying handwritten binary characters. The researchers found that a lightweight backbone like Conv4 with minimal regularization was super efficient and performed exceptionally well.
But if you take that same lightweight Conv4 and force it to process Mini-ImageIt,
Which has rich, high-resolution RGB images of all sorts of classes.
its performance just tanks.
It tanks compared to the deeper, heavier ResNet architectures.
So the takeaway is crystal clear. Structural needs are not universal.
Not at all. Using a huge ResNet on a simple task like Omniglot means you're just wasting thousands of neurons and burning compute cycles.
And the reverse is also true.
Right. Using a small Conv4 on a complex Mini-ImagineIt task means you're under-parameterized and you fail to capture all the rich features. This confirms FNS isn't just a nice-to-have. It's essential.
Essential to avoid both overfitting and just, well, ridiculous computational overhead.
So if FNS is the goal, We really need a rigorous mathematical target for what a successful, flexible network actually looks like.
Okay, so they define some core properties.
Yes, the research outlined three indispensable properties, or pillars, that FNS has to possess. It's all about finding that balance between complexity, task needs, and performance.
Inspired by the brain's own resource allocation.
Exactly. Pillar one is frugality.
Frugality. Why is limiting resources so important here? I thought meta-learning needed a big initial model.
It does. But frugality requires that for any given task, the model activates only a small, sparse subset of its neurons. It's about limiting the working parameter dimensions.
Why is that so critical?
Because meta-learning is often used in few-shot scenarios, where you only have a tiny amount of data for the new task.
Right.
If you throw a massive number of parameters at a tiny data set, you will immediately overfit. You'll just memorize noise instead of learning general patterns. Frugality directly pushes back against that risk.
That makes perfect sense. You limit your complexity to the data you have.
Okay, so pillar two is plasticity.
Mm.
This sounds like the direct connection to the BNS. Why can't a frugal model just reuse the same small, effective set of neurons for every single task?
That's what we'd call structural compromise. Plasticity demands that the activated neuron subsets must vary significantly across different tasks.
So they have to be different.
They have to be. If you're learning to classify, say, binary characters one moment, and then complex 3D object poses the next, the required feature sets are completely different.
Okay.
If the model is lazy and just reuses the same structure, it ends up with this one compromised setup that isn't optimal for either job. Plasticity forces the structure to adjust.
And finally, pillar three, sensitivity. So if you're only using a small, frugal subset, you have to be absolutely sure they're the best ones for the job, the A-team.
Absolutely. Sensitivity requires that the activated neurons are the most effective ones. They have to act as a reliable proxy for the entire network's potential.
So this is the guardian of accuracy. It is. It's the property that ensures that while we're being efficient and changing structures on the fly, we never sacrifice the final performance. It balances efficiency with accuracy.
Okay, so now we move from the theory, the why, to the practical how. How do you actually program a rigid neural network to suddenly start showing frugality, plasticity, and sensitivity?
Right. You need a system that can manage its own resources.
And that's where Neuron ML comes in with a really clever tool.
That tool is the learnable structure mask, which they call $.
A mask?
Yeah. You can visualize this mask as a layer of highly sophisticated on-off switches, and they're aligned exactly with the network's original parameters, its weights, which are theta.
Okay, so the mask controls the weights.
The parameters that are actually used for any task, DataML, are simply the original weights multiplied by the mask. So each little element in dollar represents a neuron's activation probability.
So the model isn't just learning what the weights should be, it's also learning which weights should even be active for a given task. But wait, isn't adding a whole second layer of learnable parameters, this mask just adding complexity right back into the system? How is this still frugal?
That is the critical insight of their bi-level optimization process.
Okay, bi-level.
The training is separated into two levels. It's structured like the inner-outer loop of standard meta-learning, but now it specifically addresses the structure itself.
So in that first level, the inner loop, what's happening?
The structure, mask, and ballers is held fixed. The switches are set. At this level, you only optimize the actual neuron weights, a letter-nubble.
So just the values.
Just the values, but only on the masked subset of parameters. So it's like standard meta-learning, but it ensures only the relevant selected resources are being tuned.
And then the game changes in the second level.
Correct. The weights, a letter, are now fixed, and we train the mask, $, using a custom measurement called the structure constraint, letter $.
And that constraint is just a combination of our three pillars.
It's the mathematical combination of frugality, plasticity, and sensitivity. This is where the model is actively forced to be efficient and flexible.
Let's break that down. How do you enforce frugality? And how do you mathematically minimize the number of active neurons?
So ideally, you'd use something called the lower dollar norm, which literally just counts every non-zero parameter. But counting every single active switch is computationally impossible. It's what we call NP-hard. So the researchers used a clever mathematical shortcut, the $1 norm.
Okay.
This is a tractable relaxation that encourages sparsity. And crucially, they tailored this so the constraint mathematically balances the number of active neurons against the actual sample size for the task.
Wow, so the complexity limit is dynamically tied to the task's difficulty.
That's smart.
Very.
What about plasticity? How do you penalize that lazy reuse of neurons between two different tasks?
Plasticity is measured by calculating the overlap of activated neurons between task A and task B.
So if the same neurons fire for both, that's bad. It contributes to the structure loss, yes. And this overlap is weighted by the neuron's historical importance, which they track using principles inspired by Hebbian rules.
Can you just briefly unpack that Hebbian idea for us?
Sure. The classic Hebbian idea is neurons that fire together wire together. In this context, it means if a neuron has high historical importance, if it's been highly activated across many different tasks, it probably represents some necessary common feature.
Ah,
So by weighting the overlap with this importance, they specifically discourage reusing specialized, highly important neurons across tasks that shouldn't share that specialization. It forces the model to find new structures.
a wonderful mechanism for preventing that structural compromise. Okay, last one, sensitivity.
Sensitivity uses these things called sensitivity scores,
Yeah.
mostly which quantify a neuron's immediate impact on reducing the task loss.
So it's a measure of importance.
Exactly. By minimizing LADI, Neuron ML ensures that the neurons selected by the mask are the ones with the highest verified impact, the truly critical resources. This is the mathematical guarantee that your efficient, sparse model performs nearly as well as the full theoretical one. And, the proof of all this sophisticated math is in the performance. Neuron ML was validated across 3 profoundly different domains:
What were they?
complex regression, few-shot classification, and high-dimensional reinforcement learning.
Let's start with regression. I saw the sinusoid example, which sounds like fitting a complex wave. What did FNS allow the model to do that others couldn't?
The standout feature was its ability to generalize from extremely limited observation points. The task was to infer the amplitude and phase of a complex wave.
Yeah.
Neuron ML could accurately fit the curve and then extrapolate that wave into the future, even when the input data points were located at only half or even just a quarter of the full input range.
That is a significant breakthrough. It's like seeing only the first part of a winding roller coaster track and being able to accurately predict the entire rest of the ride.
It speaks directly to the structure's advantage. It rapidly allocates the necessary neural resources to identify the core periodic structure and phase, and it ignores all the extraneous detail.
And in classification.
It achieves superior performance across standard few-shot tasks, like Omniglot. And crucially, it also excelled in multi-domain few-shot learning, using that challenging metadata set.
Right. And that environment tests the model on both in-domain and completely out-of-domain data.
Correct. And performing well on ODE data shows that the FNS isn't just, memorizing things within its training set. It's achieving a robust structural generalization.
And finally, they applied it to reinforcement learning.
Yes, using complex high-risk environments like Kazad Dome, which has noisy discrete actions, and Mujoko for continuous control of agents like Half-Cheetah and Humanoid.
So what benefit did that structural flexibility give them in environments where stability is everything?
So while Neuron ML achieved comparable or even superior average returns, the most telling thing was the return curve itself.
How so?
On these high-risk tasks, the curve was notably robust and smooth. This suggests that the dynamically adjusted structure leads to greater stability. It helps prevent those catastrophic failure modes you often see when a fixed network struggles with noise or sudden shifts in the physics it's trying to control.
That's a huge indicator of real-world applicability, stability under pressure. And did the ablation studies prove all 3 constraints were necessary?
They did. The researchers confirmed that if you remove any single pillar, frugality, plasticity, or sensitivity, you get a measurable and significant drop in accuracy. And the whole system proved highly robust, showing minimal variation in accuracy even when they tweak the hyperparameters. So the mechanism is reliable.
So, to quickly summarize this deep dive, we've pretty much confirmed from the source material that the fixed network structure of traditional meta-learning is the key thing holding AI back.
It's the primary constraint, preventing it from achieving that swift, flexible adaptability we see in the human brain's BNS.
And NeuronML provides a working model to solve this. It uses a learnable structure mask guided by that bi-level optimization.
And that optimization is powerfully constrained by demanding frugality, which is using minimal resources, plasticity, changing structures for different tasks, and sensitivity, making sure only the highest impact neurons are selected.
So what does this all mean for the roadmap of AI development?
I think this work represents a formal technical step towards integrating biological resource regulation into machine learning. This kind of flexibility, it fundamentally changes the paradigm.
How so?
Instead of relying on brute force training, these fixed, massive, over-parameterized models that waste computation on every simple task, we are moving towards systems that can selectively and optimally allocate only the most essential neural resources for the problem at hand.
A much more efficient approach.
If we can reliably achieve this dynamic structural adaptation, it addresses a major theoretical roadblock. And you have to ask yourself, when AI can stop relying on massive fixed structures and can tailor its very architecture to every challenge it faces, what limitations truly remain on the path toward general artificial intelligence?